In section 2.2, we'll be discussing the derivative. The goals of this video are going to be to define the derivative as an instantaneous rate of change. We'll discuss different ways to notate taking a derivative, and we'll also discuss interpreting the derivative. So the derivative of a function f at a point x, f of x, where f of x is the y value at x, is the instantaneous rate of change. The derivative is the slope of the tangent line to the graph of f at the point x, f of x. The derivative is the slope of the curve f of x at the point x, f of x, so tangent line slope, because it's a line. A function is differentiable if its derivative exists at x, f of x. For notating the derivative of y equals f of x with respect to x, it's written f prime of x or y prime, or for Leibniz notation, dy dx or df dx. The notation that resembles a fraction is called Leibniz notation. It displays not only the name of the function, f or y, but also the name of the variable, in this case, x. It looks like a fraction because the derivative is a slope, so it's a rate of change where it's the change in y with respect to the change in x, and so the fraction tells you that you're taking a derivative of a function with respect to a given input variable, in this case, x. We find the derivative of a function or take the derivative of a function or differentiate a function. We use an adaptation of Leibniz notation dy dx to mean find the derivative of f of x. So d dx of f of x can be written as df dx. The formal algebraic definition is the limit as h approaches 0 of f of x plus h minus f of x all over h. You simplify this until there's no h in the denominator and then take the limit, and that would be the derivative of f at x. So let's take a look at finding the derivative of the function f of x using this limit definition. So we're looking at 8 minus 3x squared. We want to start by calculating the slope of the secant line. That's what this notation m sub secant. A secant line is a line that crosses through a curve at 2 points. This is different in that a tangent line will only touch a curve at 1 point. So we start by calculating the average rate of change between f of x plus h and f of x, and then that gives us the slope of the secant line. As that h value approaches 0, the secant line approaches the slope of the tangent line. So let's start by finding the quantity. This is called the difference quotient too, just for the sake of giving you calculus definitions. So let's find the difference quotient for our function f of x. So let's start with f of x plus h. So everywhere there's an x in our function, we're going to plug in the quantity x plus h. So 8 minus 3 times the quantity x plus h squared. So everywhere there was an x in the original function, we plugged in x plus h, and now we'll expand x plus h squared and simplify this expression. Now we'll find the difference of f of x plus h minus f of x. We end up with the quantity negative 6xh minus 3h squared because the 8 and this negative 8 cancel, and negative 3x squared plus a 3x squared also cancels, and we're just left with those two terms. Now we'll take that ratio, put it over h, and simplify. So we're looking at negative 6xh minus 3h squared over h. We can factor an h from the numerator. The h's divide, and we're left with the quantity negative 6x minus 3h. That is our slope of our secant. For part B, we'll determine the slope of the tangent by taking the limit as h approaches 0 of the slope of the secant line that we found in part A. We're looking at the limit as h approaches 0 of the quantity negative 6x minus 3h. Notice that negative 6x minus 3h, the limit is only for h. We won't evaluate x, just h. That's what the limit definition, the limit notation is telling us. It is a linear function, and so you can use direct substitution because linear functions are continuous everywhere, and you're allowed to use direct substitution for continuous functions in their limit form. And so what we end up with is negative 6x minus 3 times 0, or negative 6x. So this tells us that the slope of the tangent line is negative 6x, which happens to be the derivative of f of x as well. For part C, so this is the slope of the tangent line, but we could also say that f prime of x equals negative 6x. Part C tells us to evaluate the slope of the tangent line when x equals 2. I'll be doing that on the next page. So remember, the slope of the tangent line was negative 6x. And so when x equals 2, that's negative 6 times 2, and the slope of the tangent line will be negative 12. Part D tells us to find the equation of the tangent line to the graph at the point 2, f of 2. So the first thing we'll need to do is find f of 2, and then we can plug in our slope and our point into the point-slope form to find the equation of the line. And then remember, the slope of our tangent line there is negative 12. So f of 2 is 8 minus 3 times 2 squared. So we're looking at the point 2, negative 4, and the slope of that line is going to be negative 12. So we'll plug into our point-slope form, and then we'll solve for y. So the equation of the tangent line to the curve f of x is negative 12x plus 20. Let's take a look at the graph on Desmos. Notice that the red curve is our original function, 8 minus 3x squared. I've also labeled the point 2, negative 4, where we're finding the tangent line, and I've graphed the green line, which is the tangent line to the curve at the point 2, negative 4. So it has a very steep slope of negative 12, and it just touches the graph at 2, negative 4. It looks like it lingers there, but if you spend some time zooming into the function, around that point, you start to see some separation, and it only touches the curve right at that point. That is why we call it the tangent line, because it just touches. Tangent actually means to kiss, so it lightly taps the curve and then goes about its business. Let's take a look at another practice problem. At what values of x does the graph of f in the graph have a horizontal tangent line? So a horizontal line would be going from left to right, it's flat. Horizontal lines have a slope of 0. So we're trying to think about where does a horizontal or flat line touch this curve with a slope 0. So what I'm going to do is draw a dotted line for us to drag around our curve. Here is my horizontal line. I'm going to let this move around my curve, and so wherever it touches it, that's going to be where it has a horizontal tangent line. So the first place we can see this occurring is when x equals 1. Let's keep moving. If I move down, I see that it also touches when x equals 3, and then finally when x equals 4. So for part A, when x equals 1, 3, and 4, f has horizontal tangent lines. Part B asks what values of x is the value of f the largest and when is it the smallest? So largest would also be when x equals 4. Notice that the peak happens at 2. That's the largest value that this graph attains. That's the value of f. The smallest value would be when x equals 3 because that graph touches negative 1, which is the smallest value that this graph attains. Finally, we're asked to sketch the graph of the slope of the tangent line to the graph of f at the point xy. So if we consider moving along the graph, we're plotting the slopes of all the tangent lines. So at first it's positive, and then it goes to 0, and then the slopes go to negative, and then the slopes reach 0, and then the slopes of the tangent lines go back to positive, 0, and then they go back to negative. So our resulting curve needs to have the same behavior. So I'm going to do this in green. So at first our slopes start positive, and then there's 0, the outputs. Then they're negative, so notice we're below the x-axis, and then they're 0 again when x is 3, and then they're positive until x is 4, and then negative the rest of the way. And so this would be our m of x, the slopes of the tangent lines to our curve y equals f of x. So here are some places where we can interpret the derivative. In general, it's interpreted as a rate of change. F prime of x is the rate of change of the function at x. If the units for x are years and the units for f of x are people, then the units for the derivative df dx are people per year, which is a rate of change in population. So notice that we're always doing the change in the function over the change in the input, or the change in y over the change in x. A graphical interpretation is for slope. F prime of x is the slope of the line tangent to the graph of f at the point x, f of x, which we've just seen a couple practice problems exemplifying this. We have physical interpretation, which would be velocity. If f of x is the position of an object at time x, then f prime of x is the velocity of the object at time x. If the units for x are hours and f of x is distance measured in miles, then the units for f prime of x would be miles per hour, which is a measure of velocity. So that could also be kilometers per hour, and then time could be in seconds or minutes. Another physical interpretation would be acceleration. If f of x is the velocity in this case of an object at time x, then f prime of x is the acceleration of the object at time x. If the units for x are hours, but f of x has the units miles per hour, then the units for acceleration are miles per hour, or miles per hour squared. And then finally, for our class, we'll look into the applications in business, and that would be marginal cost, marginal revenue, and marginal profit. So oftentimes when you see the word marginal, you want to think take a derivative. So marginal will imply that there needs to be a derivative because we're looking at the rate of change. So we're going to explore these terms in more depth in a later section. Basically, the marginal cost is approximately the additional cost of making one more object once we've made X objects. If the units for X are bicycles and the units for f of X are dollars, then the units for the derivative f prime of X are dollars per bicycle, or the cost per bicycle. In business context, the word marginal usually means the derivative or rate of change of some quantity. Suppose P of T is the number of individuals infected by a disease T days after it was first detected. We're asked to interpret P prime of 50 equal to negative 200. Since P has units of number of individuals infected and T has the units for days, the units for P prime are going to be the number of individuals infected per day. So P prime of 50 equals negative 200 says that after 50 days, the number of people infected is decreasing by negative 200 people per day. In the next video, we'll review some rules to take derivatives without using the limit definition.